Hi, my name's Phil Torino, and I'd like to welcome you to Hack with Phil. I'm a little bit new to this whole video blogging thing, so please bear with me if you would. Today I'd like to show you a little project that I have involving my desk lamp and its power supply. So thanks for watching. So I have my desk lamp here, and it's been an absolutely great desk lamp. It has a built-in magnifying lens and everything, and it's run on all these LEDs that I've actually tested this. They only draw about 12 watts, which means you could run the lamp for an entire month on probably about $1, never turning it off for the entire month. That's pretty cool. But the thing's only maybe a couple of years old, and just recently it started flickering when I would turn it on. It would flicker for maybe 10-15 seconds and then all of a sudden turn on. And it's gotten worse just recently to the point where when I turn it on, it'll flicker for maybe about 2 or 3 minutes and then all of a sudden it would just come on, which is kind of annoying. So I decided to take it apart and see if I could find the problem. When I first opened up this little casing over here, right, I found the circuit board, which is the power supply circuit board. It takes mains voltage and turns it into DC. I noticed on the circuit board that there was a bad capacitor, and I removed the bad capacitor and went ahead and replaced it with a Rubicon capacitor that I pulled off one of my old circuit boards. And I had everything all plugged back together, getting ready to do my victory dance when I turned it on. Everything worked, and it still flickered. So I went through testing each component on the board and eventually got to this guy over here, the transformer, and found that the resistance across the primary leads was on the order of a couple of megohms. So that thing's blown. And I don't really have a replacement for it, so what I decided to do was to build my own variable voltage DC power supply and have it so that I can adjust the brightness on these LEDs rather than just have it in either an on or off state. So now the question is, how do I design my circuit? I came up with the idea to use an LM317, which is a pretty jelly bean component. You can even get them over at Radio Shack. It's a voltage regulator that is based around an operational amplifier, and you can adjust the output voltage by adjusting the resistance in a voltage divider in the feedback. My design starts off with something that's pretty generic, just some small modifications. You have your mains 120 volts coming in here, goes through a transformer. That's going to drop down to 24 volts at this point. But that'll still be AC until it goes through rectifier over here, a full wave rectifier, and comes into the LM317. We'll have a capacitor here to sort of smooth out the voltage that's going into the LM317. That'll have quite a bit of capacitance on it. And coming out of the 317, we'll have our feedback loop, which will normally consist of 2 resistors, right? And you tap the middle of the voltage divider and feed that back into the LM317. But to make it adjustable, what I'm going to do is throw in this potentiometer over here, this 10K potentiometer, or possibly, if I can find one, maybe a 1K potentiometer. I'll play around with the math a little bit and see what works. And before I start playing around with the math, one thing that's very important for me to know is what this V out has to be, what it has to produce. So V out has to be between what 2 voltages? What should I put over here? So I have my power supply set up here. I'm limiting the current to 500 milliamps, or half an amp, and I have the voltage initially set to 6 volts. And I have it hooked up to my board over here on the LEDs. So I'm going to go ahead and switch that on, and we'll gradually increase the voltage. 8 volts, 9, 10, 11, 12, 13, 14, 15, and we have light. It's not very bright, but we have light. And we'll see how far beyond 15 we need to go in order to get a good amount of brightness out of this. So we'll try 16, and we get a little brighter. 17. 17 actually looks pretty good. I think 17 will be a good running voltage. And 18, it's pretty bright. Now let's try 19. It's very bright. And at 19 we're drawing 0.25 amps, a quarter of an amp. Alright. I don't think I should run it very long at 19. Maybe 18. At 18 we're drawing 180 milliamps. And at 17 we're only drawing 100 milliamps. I think that's about where it used to run, is at 17. So when I design this supply, I think I'm going to design it to put out voltages between 15 and maybe up as high as 18.5 or 19 volts. Hi there. So coming back from the power supply, we figured out that V out has to be somewhere in between 15 and 19 volts. So what does that mean? We need to pick particular values for R1 and R2 such that when the values are just R1 and R2 and this 10K potentiometer is 0, we get 15 volts. And when the values are R1 and R2 plus this 10K potentiometer, meaning that we turn the knob all the way up, we get 19 volts. Alright, so how do we figure out what those two values are? Here's where we head back to math class. So looking at the LM317 data sheet, we find this formula which states that the output voltage is going to be equal to whatever our reference voltage is times 1 plus R2 over R1 plus the current coming out of the adjustment pin times R2. Now the current coming out of the adjustment pin is very, very little. So we can almost equate this thing to 0, and to make the math a little bit simpler, we're just going to ignore this term. Because it's so close to 0, we can do that. Yeah, our numbers are going to be a little bit off, but not by much. Alright, and for the reference voltage, you find this in the data sheet as well. The reference voltage is nominally 1.25 volts. Alright, so I put that in 1.25 volts over here. I want my output voltage to be 15 volts, and I'm multiplying this by 1 plus R2 over R1. Except I've modified this. I made this adjustable by putting my potentiometer into the voltage divider, and it's in series with R2, so that means that when I turn the potentiometer all the way up, it goes up to 10,000 ohms. That 10,000 ohms is going to get added to R2. And then I'll divide that by R1, add 1, multiply by 1.25 volts, and that should come out to 19 volts. Alright, so here I've modified the system of equations just a little bit. I've multiplied everything through by R1 on both equations to get rid of the fractions. Now to modify this a little bit more, I'm going to do the subtraction. 15 minus 1.25, I get 13.75. And 19 minus 1.25, I get 17.75. And that's my coefficient for R1. Then for R2, I'm going to subtract both of these over to the other side of the equation. And I have 1.25 for each of those. That's my R2. And then on the right-hand side of the equation, I will have a 0 and 12,500. So I have here my augmented matrix, and I'm going to put that into reduced row echelon form, which I'll use computing software for because I'm lazy. Okay, so I worked out the solution to the system of equations. And I was kind of crossing my fingers because there is a little bit of a restriction on the values that you can choose for R1. What happens is if R1 gets to be over 1,000 ohms, the voltage regulator, the LM317, becomes very unresponsive, starts acting funny. So you usually want to choose R1 to be somewhere between 250 ohms and 1,000 ohms. In fact, I think on the data sheet they even say go as low as about 220 ohms. So I'm going to have to modify the circuit a little bit, because the values that I'm getting over here, they give me a value for R2, but the value for R1 is 3,125 ohms. That's a problem. So I'm going to have to redo this. Okay, so what I'm going to do here is investigate what would happen if I used a different potentiometer, something other than my 10K potentiometer that I was looking at before. So what I'm going to do here is I'm going to copy that system of equations, that matrix, and I'll do paste down here. And the only thing that changing from a 10K would do to, say, a 5K would be to cut this in half. So what I can do is change this to a 6,250, and let's go ahead and evaluate that, see what happens. Oops. Get rid of that. And let's go over here, put this into reduced row echelon form. Solvers and forms, row echelon, reduced. And I see here that I'm getting from a 3,000 ohm resistor to a 1,500 ohm resistor. Alright, that's an improvement, but still not where I need to be. So I'm going to try this again. We'll go down here, we'll do paste, get rid of that, and let's see what would happen if we used a 1K resistor instead of a 10K potentiometer. I need to go over here and select reduced row echelon form, and here I have a 300 ohm resistor now, well, 312.5 ohms I would need to use for R1, which is acceptable. It's in that 200 to 1,000 range. So that's doable if I can get my hands on a 1K potentiometer. Alright, but we are going to look at other possibilities, because I don't know if I want to take a trip down to Radio Shack right now. So I have an idea for modifying the circuit, which I'm going to go over in just a second, where I could maybe still use that 10K potentiometer, which I have a whole bag full of them. I don't know if I have any 1Ks at all, though. Hey, so my idea to fix the problem would be to throw in an extra resistor right here, in parallel with R2 and the 10K potentiometer. I'd still be able to use a 10K potentiometer, but now with this extra resistor, when I swing this by 10,000 ohms with the extra resistor in line over here, the overall resistance is only going to swing by maybe 5,000 ohms or 1,000 ohms, depending on what value I choose for this R3 over here. Alright, if you remember how to calculate resistances when they're in parallel, all you have to do is take the product of the two resistances, so R2 plus 10K and multiply that by R3 and divide by the sum, which would be R2 plus 10K plus R3. Or the other value for the resistance would be, if 10K was 0, in other words, if I had the potentiometer turned all the way down, I'd have R2 times R3 over R2 plus R3. Okay. And those would be my two new values for the resistance. And what I can do is choose R1, this way I don't have too many variables floating around here. Remember, I'm only going to have two equations, so it helps if I only have two unknowns. I think what I'm going to do is choose either 220 or 240 for R1. Alright, so I'll say that R1 is equal to 220 ohms, let's make it. Alright. And I'll use those two equations for R2 and R3. Okay, so just a little recap here. I added in R3 to my network, which the data sheet normally refers to just as R2, but now I have R2 10K potentiometer and R3 in parallel with that. I've fixed R1 to 220 ohms, and what the data sheet refers to as R2, which is basically the south end of the voltage divider that they use in the feedback loop for the LM317, that is now either R2, R3 over R2 plus R3, or if the 10K potentiometer is turned all the way up, you have R2 plus 10K times R3 divided by R2 plus R3 plus the 10K. Alright, so I've taken this information and plugged it into the equation that we find on the data sheet for the LM317, and plugging that stuff into the equation, it looks like this. Alright, and this system of equations is not a linear system of equations anymore, so I can't really use matrices to solve it the same way I did the last one, but I can do substitution. Alright, so what I do is I take the first equation, this 15 volts equals 1.25, 1 plus R2 R3 over 220 R2 plus R3. Alright, I take that and I solve it for one of the variables. I chose R2. So what this involves, I think first I want to distribute the 1.25 over the parentheses, and maybe go ahead and subtract the 1.25 from both sides of the equation. And I could also clear out the R2 plus R3 that's on the bottom of the equation that we see right over here. So I'll go ahead and multiply through by the R2 plus R3, and what I end up with is this guy down here. Back out just a little bit. Alright, so I have 13.75 R2 plus 13.75 R3. So I went ahead and just combined the 15 minus 1.25 and 15 minus 1.25 for the R3 as well. I did it for the R2 and the R3. And there's a 1.25 in front of the R2, R3 over 220, because remember that also gets distributed. And what I do over here is I get the R2s by themselves on the left-hand side of the equation and factor out the R2, and I move the R3 over to the right-hand side of the equation. And then all I have to do is divide, and I get this mess. But that mess actually cleans up fairly nicely if you can finagle the fractions a little bit. Right? You get that R2 is equal to R3 over 2420 minus 1. Or we can go ahead and make it just a simple fraction by multiplying top and bottom by 2420. And we get that R2 is equal to 2420 R3 divided by R3 minus 2420. Very nice. And all we have to do is take that, and in the second equation, remember the second equation up here, 19 volts, anywhere that we see in R2, we replace it with the 2420 R3 over R3 minus 2420. So let's go ahead and do that. Okay, so plugging into the second equation, having first distributed, in my second equation, having first distributed the 1.25, subtracted 1.25 from both sides, so I get 17.75. And I'd have 1.25 in front of the R3 right there. And 1.25 divided by 220 simplifies to 1 over 176. Alright, so that's where that 1 over 76 came from right there. I'm plugging into the second equation. That's what I get, that little bit of a mess right there. And I go ahead and clean up the mess, mostly by multiplying top and bottom of the equation by R3 minus 2420, and getting whatever terms I can to cancel out. And so I have that 17.75 equals that fraction right there. And you see you got some R3s, you got some R3 squareds. So all I'm going to have to do is multiply both sides of the equation by the denominator and get the thing set equal to 0, and what I'll have is a nice quadratic which I can then solve. So I went ahead and ran the numbers, and my quadratic is this guy right over here. Negative leading coefficient means it's an upside down parabola. Probably crosses the x-axis at 2 different points, and the x-axis in this case represents R3. That's what we're solving for. And we got that R3 is equal to 2,110 ohms, as well as 3,853 ohms. There are two solutions. But if we use the 2,110 ohms, it's going to cause a problem when we go and try and find a value for R2. If you remember, in order to get R2, I'll look back at our board over here. Okay. Zoom in on that right there. We said that R2 is equal to that guy right there. 2,420 R3 divided by R3 minus 2,420. Now, if R3 is less than 2,420, that's coming out to a negative number, which is a problem. We can't use a negative value for our resistors. We need that to be positive. So, zooming out there, alright, and looking back over at our computer here, if I have to choose between these two values, I'm going to choose this value right over here, 3,853. Alright, so that's my R3 value. And I'm going to go ahead and plug that into that formula in order to find what R2 is, and I find that R2 is equal to 6,506 ohms. Concluding this segment, we found that if we make R1 220 ohms, we would have to use 6,506 ohms for R2 and 3,853 ohms for R3, and then we could use our 10K pot and have the voltage swing between 15 and 19 volts. In my next video, we're going to build this circuit up on the breadboard and see if we can actually get it working the way that the math says it should. And if it does, we'll try and implement it, build it up, and see if we can get the desk lamp back in operation and I can start doing more projects. Thanks for watching, and have a nice day. Hi. That's too perky.